My goal in introducing these different bioprinting strategies is so that we can better understand the advantages and disadvantages of each, as well as the potential applications and kind of what we're doing with these different applications. So with that in mind, if anybody has anything they'd like to add to any of these techniques, this would be a great time to discuss that. And I think really one of the best ways to get to learn how to use these techniques or what these techniques are good for is to talk to somebody who has used them. So again, that's something I'm going to encourage, as we move on with today, as well as later during lunch, and when you get to see kind of the biomaterials lab upstairs, and when you get to see some of the applications that researchers are working on there. So just to be on the same page with our definitions, bioprinting, as I refer to it, is going to be 3D printing with cells and/or active components. So anytime that we've moved beyond just 3D printing a scaffold that's inert or an object that is to be used as just a surgical pre-planning model, I'm going to refer to that as bioprinting. And you'll hear a lot about bioinks. In this case, bioinks are not just the biomaterials we're using, but it's the inclusion of cells and bioactive components. A bioink does not necessarily have to have cells in it, but there's got to be something in it that has a biological purpose to encourage cellular growth, differentiation, some type of tissue function. We're going to cover a variety of different techniques, and all of these techniques that I'm talking about in this particular discussion will be techniques that you can actually employ cell populations into, and techniques actually that we have access to in the biomaterials lab. We'll be talking about everything from extrusion-based printing to droplet inkjet printing, as well as laser-based or light-based printing in stereolithography, digital light projection, and laser-induced forward transfer. So to start with, inkjet printing is probably one of the most familiar aspects of 3D printing and bioprinting. It's perhaps one of the most accessible because all it takes is access to a traditional inkjet printer and being able to customize manufacturing your own head. And because of that, it's often the most affordable, easiest way to get into 3D printing for the past several years until the advent of some of these cheaper extrusion-based printers have started to take over. But the basic principle, which is really important to keep in mind in inkjet printing, is that we're producing in a heater-based inkjet head a bubble that provides the pressure that pushes out droplets of our bioink. And in the case of a piezoelectric actuator, we're using a piezoelectric ceramic in each nozzle that provides a transient pressure to eject ink drops onto the substrate. The mere fact of creating these pressure bubbles and pushing out these cells has a drastic impact on our cell populations. So it's important to consider a number of different factors if we're going to use these techniques. And it's important to consider whether or not we can actually use this technique on our cell population. The very first consideration is that of cross-linking and gelation of the material. So we absolutely need our bio ink to actually cure after we print it. If we're just spraying out liquid in an inkjet and you're trying to come up with a 3D structure, you're obviously not going to come up with multiple layers if all you're doing is spraying a liquid. So it's really important that we use a material that gels, and it gels fast, or it cross-links fast. This may mean that we increase the viscosity of our material itself, or it may mean that we incorporate some kind of cross-linking moiety that enables us to immediately cross-link or gel that material after it's been ejected from the inkjet head. The nozzle geometry and printing speed of inkjet printing also drastically affects not just the resolution and the gelation of our scaffolds, but it does affect the thermal and shear stress on materials and cells as well. So we'll see some research that actually investigates nozzle geometry and printing speed. And these also affect, uniquely in inkjet heads, you see problems with blockage of those heads, which of course can ruin prints really easily and are of course very annoying. And so getting the right geometry, getting the right printing speed is really important to be able to efficiently produce our scaffolds using this technique. Like I mentioned before, viscosity is extremely important, and again, viscosity is something that's a common theme in 3D printing. It's got to be necessarily low for inkjet printing. Perhaps inkjet printing is one of the techniques in which we need the lowest viscosity of our materials in order to actually print those out of the head. And so that does limit our material choices. With thermal printing, we can produce droplets with relatively good cellular viability, and that process has been around it's one of the processes that has been around the longest in 3D printing, so it's fairly well understood. But even with our understanding of thermal inkjet printing, you often get mixed, unordered, or unequal in size droplets, which can drastically affect the resolution of your 3D printed scaffold, as well as even the viability of the cells long term. On the other hand, piezoelectric printing droplets generally are more regular and equal in size, so if resolution is something that's important to you and predictability of the scaffold, then piezoelectric printing is a good way to go, but there have been several studies that have noted the reduced viability of cells produced with piezoelectric printing. But again, this can all be affected by adjusting things like the geometry of your nozzles when you're using inkjet printing. So like I said, typically these processes are going to be low cost, and they're well known to support the viability of cells, although there are still some challenges that exist with things like nozzle geometry and trying to accommodate the viscosity of our materials. And thermal-based cartridges, while found to be reasonably amenable to cell viability, also allow multi-material fabrication. So it's relatively straightforward to print with multiple materials, just as you see in a normal inkjet cartridge using different colored inks. The same can be said for inkjet printing. So it's cheap, easy to incorporate different materials, which is really important when considering those hierarchical structures of tissue engineering scaffolds we mentioned in the last presentation. But like I said, some of the disadvantages here are the effects that we might have on cell viability, especially in the case of piezoelectric cartridges. There's also been a noted phenomenon of pore development in cells that are printing 3D printing because of the shear stress effects on these cells. However, there's also research that utilizes these pore developments in these bioinks by incorporating things like genetic engineering or drug delivery, so you have a perfect time for cells or to encourage uptake of these factors during that printing process. So that disadvantage can actually be turned to an advantage, and you will see some research that uses that. But the inks that we're using do have to be low viscosity, which, like I said, drastically limits material choices. And we'll talk more about how these material choices affect our prints, which may make inkjet printing something that you're not interested in, depending on the type of tissue that you are trying to produce. And finally, it's extremely important in inkjet printing that our gels are produced quickly and they cross-link quickly. So there's a variety of materials. This is not an all-inclusive list, but during each of these techniques, the materials that I'm presenting here are widely researched, so if it's something that you haven't seen, I encourage you to check it out. But in inkjet printing, people have printed with anything from hydrogels to actually using DNA or just cells in suspension. The applications that you're going to see in research a lot in this case is for cell patterning effects, as well as producing organoids and blood vessels. Those are seem to be the best case scenarios for using inkjet printing. And there have been a couple researchers who actually developed inkjet printing methodologies for in situ printing. The next kind of logical step from our inkjet printing is extrusion-based printing. So in this case, we're using some kind of force to push a polymer or a polymer solution with our cells out of an extruding head, whether that's pneumatic, piston, or screw force. And all of those have their own advantages and disadvantages. But one of the great things about extrusion printing is that you reduce some of those shear stresses that inkjet printing has on cells, which increase the viability of cells produced through these printing, as well as you avoid clogging, and you don't have to worry so much about thermal conductivity of an inkjet head, since we aren't using any kind of heating elements directly on many of these bioinks that are used in this type of printing process. However, because we're using extrusion and because we have a wide variety of materials to choose from, you're going to have a very hard time finding an extrusion printing methodology right now that can produce fibers consistently with live cells below 100 microns. So the diameter is often going to be a little bit larger in extrusion printing than something like inkjet printing. We also see extrusion printing a lot in fused deposition modeling. In this instance, you're likely not going to be including cells because you use a solid feed material that's melted through deposition and assembled through extrusion and cooling. So this is really great if you want to use polycaprolactone, for instance, and you want a scaffold that has high mechanical strength, and you also don't have to include a solvent because you're just melting down this polymer. So the scaffold itself might have great cell viability for those reasons, but the high temperatures required for melting are going to make it prohibitive to include many bioactive factors and cells. However, we are going to talk about later some strategies we can use to increase the bioactivity of growth factors and drugs if we want to include them in fused deposition modeling, which is why I'm including this here, even though it's not compatible with our bioinks with live cells in almost all cases. So if you are interested in printing with cells, you're likely going to rely on some kind of solution-based deposition. This might be using a hydrogel as the basis of your bioink, and the scaffold deposition still takes place through an extruded solution that starts off as a gel or liquid. And this is going to be the best way to support the inclusion of growth factors in cells because we don't have any kind of thermal stress on our constituents. In this case, there's a few different strategies that are going to vary drastically based on both the material choice of your bioink as well as the type of printer that you're using. So you might be limited in which of these cross-linking methodologies you can use. The simplest is to first use extrusion printing to deposit material into a cross-linking reservoir. So imagining having a tissue culture dish full of calcium chloride solution, for instance, and then as you print an alginate liquid solution here, it cross-links into your scaffold as it's deposited into that reservoir. You might have a separate nozzle that incorporates a cross-linker after you print it, in which case you can print in a dry environment, but it is kind of difficult to find a printer that's going to have two nozzles that can be used directly at the same time if you're going a commercial level. So this might require either an open source printer or modifying a commercially available printer. On the other hand, we can kind of make this a little bit simpler by using a pre-cross-link bioink. So you'll actually see a lot of people use different methodologies to pre-gel, for instance, a gelatin, and then further cross-link that after they print it. So you at least have some structural formation, some gelation prior to printing, which increases the resolution of your print and prevents that liquid from just spreading across your printing reservoir. One thing that is becoming more common is using a coaxial nozzle, or even not just a coaxial nozzle, but using a multi-material print head that mixes the material as it's printed out. So as these materials mix, when they leave the nozzle, they're cross-linking. This is something that you'll see in some custom applications, and there are just now some commercial printers that have this availability. And finally, if you have a bioink that you can use an aerosolized cross-linker to cross-link that either layer by layer, that is another opportunity. We also have photo cross-linking, whether that's UV or visible light cross-linking, that are available in many of these 3D printers. So when you're using extrusion printing, and again, like inkjet printing, one of our main concerns is cross-linking and gelation speed. Even with adding these cross-linking agents and these multiple methods that we will use, we're still very concerned about the speed to maintain the structural integrity of our print. And we also need to ensure that the methodology that we use for cross-linking is compatible with our printing process. Another thing that I'll talk about in the next slide here is the shear thinning effects that these materials have. Often, since we're working with higher viscosity materials, we'll be working with materials that impart shear stresses on cells as they are printed out that extrusion nozzle. So that drastically affects the cell viability, as well as the gelation of the material when it's printed. We're going to go into just a brief intro into that in the next few slides, but later presentation will dig much further into how shear thinning can affect our cells, as well as how we can affect shear thinning to improve our printing process. The extrusion and printing speed, of course, is important to consider on the integrity of extruded fibers. So just by adjusting the printing speed, you'll see we can drastically affect the material that we're printing, the integrity of the print as it's related to the desired outcome, as well as cell viability. And viscosity is going to be our next talking point, like I mentioned. And viscosity will be drastically affected by gelation as well as temperature. Again, viscosity goes hand in hand with the shear thinning effects, as well as the actual cross-linking and gelation, maintaining structural integrity. So a lot of these properties are going to interact with each other back and forth. And so often when you're developing a bioink, you'll find that you have to compromise, and there may not be a perfect solution that handles all of these aspects. And that's where you need to decide what the most important aspect you want to focus on is. And finally, with extrusion printing, is we need to ensure that somehow the first layer is anchored onto our tissue culture dish. So for instance, I've had this happen time and time again, where when you print this first layer, let's go back to my alginate example, where somebody has a cross-linking reservoir of calcium chloride, and they're ready to start printing their alginate directly into that. As soon as that alginate hits the calcium chloride, it starts to cross-link. So unless you have a really good way to make sure that you're printing the calcium or the alginate onto the bottom of the dish, and that it's actually sticking to the bottom of the dish, you're just going to end up with this floating mass of alginate. Similarly, you'll find that in some of our discussions later, it's really important that we figure out how we make this bottom layer adhere to even just a dry dish. So that's something that a lot of people, when they're jumping into 3D printing for the first time or getting to their scaffold, don't consider at all. And then it turns out to be a huge challenge because you've designed the material, you've designed the bioink, you think you've got perfect compatibility, you've got the cross-linking agent, but nobody considers that first layer anchoring, and then all that work you've done is for nothing. So if you haven't used 3D printing yet, and you're planning on using a hydrogel or some other type of biomaterial in extrusion-based printing, I strongly encourage you to consider how you're going to get that first layer to stick and how you're going to get that first layer to stay in place. So as I promised, one of the things that we're interested in here is gelation and how shear thinning and shear forces affect the bioinks. So in this case, we can see just an example of when the gel is just in our syringe, for example, how the gel is relatively relaxed, and as soon as you apply pressure to squeeze that through a nozzle, you start aligning fibers, and so you can imagine for the cells that are in here, you're getting actual fluid flow, which imparts some of those shear thinning effects, and then as you print that out, you go back to a more relaxed state and an entangled state. It's absolutely important to consider, how this transition affects the viscosity of your print, as well as how that'll affect cells. And like I said, we'll get far more into that later. But on a material and printing methodology level, we can also drastically affect the integrity of our print by altering things like the velocity at which the extruding nozzle is going across our substrate, as well as the height between the nozzle and the plate. So when you go up in the lab, you'll see some demonstrations of this later. But if you look at this single fiber that's produced here, for instance, just by changing either the velocity going across our substrate or the height from the nozzle, you can drastically affect the extruded fiber. So this is all the same material. This is one print. And you can see you get this coiling in the material. And if you are going too fast, if the nozzle is too high, you can get this pulsed fiber, so you lose structural integrity. So again, when you're designing a biomaterial or you're designing your bioink, it's not just the materials and the cells that you have to consider, but it's all these little factors that you have to make sure you have time for, you accommodate when you're printing, because you will never produce a scaffold with good resolution or the size and geometry you're looking for unless you really narrow down these parameters. So just to wrap up on the extrusion printing, it's extremely good for rapid prototyping if you're just using fused deposition modeling. And we have a variety of ways that we can set materials, whether it's through temperature, photo cross-linking, chemical cross-linking, or simply using pre-gelled hydrogels, in which case they're simply viscous enough to form structures upon deposition. That gives us a huge breadth of materials that we can incorporate into various extrusion techniques. And we can fabricate basic scaffolds for tissue engineering applications because we do have several different options for printing with cells or growth factors directly. And like I said, this kind of goes in line with using some of those thermoplastics, but for instance, we can get very good production of really strong, structurally sound geometries and objects, which is kind of unique to extrusion-based printing when compared to inkjet printing and a couple of the other methodologies that we'll talk about later. And of course, with a lot of these extrusion-based printers, it's really easy to incorporate multiple materials. This is going to be absolutely crucial to some of the important strategies that we get to in the next several slides in the lectures. The disadvantages, of course, are that materials still have to have low enough viscosity to be deposited, and likely you're going to be working with materials that do have some kind of shear thinning effect. So the viscosity changes as the shear rate changes on our materials. The resolution and feature size of extrusion printing is often limited, and like I said before, we're looking at fibers that are generally no smaller than 100 microns in diameter. So you have to be willing to sacrifice a lot in the way of that microscale architecture design if you're using extrusion printing by itself. And if you're using high temperature techniques such as fused deposition model, it's going to be very difficult to incorporate cells, growth factors, or other bioactive substances, although there are some workarounds that, again, what we're going to talk about later that I think are very interesting. And finally, the solidification rate varies drastically. You saw some of the issues too with if we don't get the right process parameters, we don't get the right structural integrity. So I'm not going to belabor all the different materials we can use. Like I said, through applications, we can go everything from surgical pre-planning and tools all the way to tissue scaffolds as complex as we want. One other interesting 3D printing methodology then is lift bioprinting. We don't directly have lift bioprinting in the Biomaterials lab, and there are probably a lot fewer labs in the bioprinting realm that use lift bioprinting compared to some of these other techniques. And the basic premise here is that we use a ribbon here that has our bioink. So this is going to look a lot different than the other two techniques we talked about. And this bioink here has whatever materials we're using as well as cells, and it's actually going to adhere to our bioprinting ribbon here. We use a focused laser then to create these air bubbles, kind of like what we're doing with inkjet printing, that will create a jet that deposits these biological layers, these bioink layers, onto a substrate. So you can see right away we're kind of limited to more or less 2D structures, but because we're using this laser to get these focused jets, we can create really fine-tuned cellular patterns on our surfaces, and we have really nice high resolution. Some of the challenges with getting this to work properly, though, is that, like I said, the vapor bubble is generated by the vaporization of that first layer of the biomaterial. And so you've really got to tune the energy appropriately, because if you have a sub-threshold regime, in which case you don't apply enough energy from that laser, you simply end up with this bubble that collapses in on itself and no material is deposited. If you put too much energy on this, you end up with a bubble that bursts, and essentially you get cellular confetti, so you're not going to get much of a jet stream from that. So it takes a little bit of fine tuning in order to to apply the right energy, ensuring that you have the right thickness of your bioink, and the material is carefully selected for, so you get an actual jet that'll give you your highest resolution possibility. With that in mind, it's extremely important to consider a couple factors, because this is a really delicate process, and you really need to consider the thickness of the biological materials on the films. Like I said, that can alter the effectiveness of the bubble formation and the necessary energy that you have to apply to get the proper jet stream. It can also control the materials deposited on the printing substrate, so the volume of your material, each layer, the layer thickness on your substrate is going to be drastically affected by the thickness of the biological material on your printing ribbon, which makes sense. Viscosity and rheological properties are important here, just as they are in the other printing methodologies, because we're going to go back to how they affect the bubble formation and the collapse of that bubble. If you have too viscous of a material, you're just not going to get an energy transfer. And if it's too viscous and you keep trying to increase the energy, you might end up essentially cooking your cells, in which case you need to go back to the drawing board and find ways to reduce the viscosity of your bioink. So that all goes back in line with the energy of the laser pulse is extremely important here, because that's what initiates our bubble formation and enables this printing process to take place. And like I just mentioned, if you don't get that right, you're either irradiating the cells or you're not printing anything. So with that in mind, laser-induced forward transfer bioprinting, the advantages you see here are very high resolution, and you can get down to a single cell level of printing methodologies. This is great if you're doing some kind of microscale cell patterning, if you're interested in microvasculature, for example, and you're willing to use just a monolayer of cells or a barely three-dimensional cellular construct, then some type of technique like this will be useful. However, there's limited printing in the z-axis, so you're not going to get these really nice tall structures that you might need if you're, for instance, printing a bone scaffold for a critically sized bone defect. And the heat generated from the laser may damage the cells or affect the cellular biology further down the line, so your tissue isn't that functional living tissue that you intended it to be. Because it is such high resolution, it does affect the fabrication time. So that's another thing that you have to consider, is how long these cells are sitting here in the bioink as well as in on the cell substrate. Again, there are a variety of materials you can use. They're very similar to the materials you'd use in inkjet printing, but the applications so far have been largely limited to cellular constructs, although there are some papers out there in which people actually use this technique for in situ printing. So if you're interested in seeing some 3D printing directly onto tissues, besides those inkjet printing methodologies that have been developed, this laser-induced forward transfer has actually been used on a couple of mouse models. So the final technique that I'm going to talk about in bioprinting for now is vat photopolymerization. This is a little bit different than the extrusion techniques because we're not depositing something onto a substrate. So in this regime, we have a tray with the material resin on top of our printer. And then below that, we have a laser light source. That laser light source will often be reflected on a mirror and then hit somewhere inside our tray with our material resin and cross-link that point. So you're necessarily working with a photocross-linkable biomaterial, in this case, that's liquid at room temperature. So already you can see where that will start limiting your bioink choices. This cures, excuse me, like I said, this cures the biomaterial point by point. And what's going to happen is this base plate starts out within your resin, and it will cure the first layer point by point of your bioink attached to the base plate. The base plate raises up a bit, and then again you cure the next layer of your bioink onto the layer that's already there on your base plate. So layer by layer, you get this construct that kind of rises out of your material. So important factors to keep in mind are that you want your construct to properly adhere to your base plate, and of course it has to be photocross linkable. You can either use UV light or visible light depending on the printer setup. In addition, a very similar technique is using digital light projection. Instead of using a single laser to do a single point at a time, you use a projector to cure an entire layer at a time. Otherwise, this works more or less the same, where you're curing a layer or curing this scaffold layer by layer attached to a base plate that will raise out of your tray with your liquid material after each layer is cured. So because Vat photopolymerization is so different than some of those other techniques we mentioned, there are some additional considerations that you want to keep in mind. In this case, like I said, photo cross-linking is absolutely integral to the success of these prints. It's also important to consider how you're photo cross-linking these materials, because very often the materials that you use with cells, while they may be biocompatible, the cross-linking agents you use to initiate those photo cross-linking reactions may have drastic effects on cell viability. So it's not just the UV or the visible light irradiation we're worried about, but also what cross-linking agents we're using and how biocompatible the material is for our cells or our growth factors before we even cure them. We also find another problem with Vat photopolymerization is extraneous cross-linking. So once you initiate a radical reaction from a photo cross-linking agent, for example, you might spontaneously set off this unintended reaction where you start curing the materials around that single point that you initially intended to cross-link. So the resolution can drastically get out of hand in Vat photopolymerization if you don't either carefully study the chemical reaction that you're setting off through your bioink, or if you don't include some kind of inhibitor that'll quench those reactions before they over cross-link your bioink. Additionally, the exposure time that or the exposure time of each layer can drastically affect not just the cell viability, but it can also be used to modulate the mechanical strength and structural integrity of your printed construct. So for instance, one material that's really popular in our lab is using polypropylene fumarate. We've used that material successfully to 3D print bone scaffolds. So you can imagine the kind of brittle bone scaffold you would expect to be printed using polypropylene fumarate with a biocompatible photopolymerization process. We can also use that exact same material using the same chemical cross-linking agents, and by simply adjusting the exposure time on each layer, we can adjust the amount of cross-linking in the material. So using that same bioink, we can form vascular scaffolds, which have far different elasticity properties, different tensile strength properties, and different compressibility. So really fine-tuning this printing process can drastically affect the scaffold that you produce, which is a reason that Vat photopolymerization might be a great way to customize an object if you're especially concerned about the mechanical strength. Like I said, the resins that you use for this are going to start out as uncross-linked moieties. And if you're including cells or any kind of growth factors or other bioactive chemicals within your bioink, you need to ensure that the uncross-linked moieties are also compatible with those components. So whereas most of the materials you're using in extrusion or inkjet printing are already hydrogels that are more or less biocompatible with the resins that you're using for Vat photopolymerization, it's extremely important that you consider what happens to the uncross-linked moieties. Again, first layer anchoring, just like I talked about in the extrusion process, is absolutely crucial, because if your object doesn't stick here, if you can't figure out the properties to make your object stick to a base plate, you're not going to be able to produce any three-dimensional object. Yeah?
So in that situation, is it common to functionalize, like chemically functionalize the base plate, like if you were doing peggy or something?
Yeah, I think there's a couple of different methods you can use, whether that's functionalizing the base plate or just using a customized base plate with the different material, increasing the surface area on that base plate through making it rougher potentially, or pre-cross-linking material to your base plate. So you might start off with a layer of PEG-DA that's cross-linked, which provides enough non-covalent interactions with the base plate for the next layer to stick. There's also in a lot of synthetic polymers, you'll have what's called a burn-in layer here, where you overexpose the first few layers of your material, which increases the adherence to this base plate. And I don't know, there's a couple students from Jordan Miller's lab here, right? I don't know if you have an answer to that too, because I know you guys use PEG, and it's in a DLP process or a stereolithography process. Are you familiar with your strategy for encouraging that material to stick to the base plate? I don't know if you work with it or not.
Yeah, so basically we increase the first layer exposure time from like the normal, it's around like 8 seconds exposure time for each layer, so around 30
Okay.
seconds. So it will be like more costly, so then I can stick firmly to the platform.
Okay. Okay, good to know. Thank you. So just for the recording's sake, for encouraging, and that's PEG-DA? PEG-DA, yeah. So encouraging PEG-DA to adhere to a base plate, your lab does indeed use the, I guess what we'd say, the burn-in layer. So increasing the exposure time for those first few layers from 8 seconds to 30 seconds, which ensures that it sticks to the base plate. Cool. Thank you. Yes. Oh, sorry. Did you have more? Okay. So does the resolution or does the digital light projection methodology affect the resolution of the print? And the answer is yes, definitely. The good thing is with a lot of the digital light projection and stereolithography, you actually have resolutions that beat the resolution you can achieve with the materials. So, for instance, some of the printers that we work with have resolution on the XY plane of about 15 microns, but often the biomaterials we work with prohibit us from getting down to 15 micron resolution. So we're looking at features of more like 50 microns. So yeah, there's definitely a hard limit with these type of techniques, but you'll find more often than not with Vat Photopolymerization that our major limit is actually in the materials. And still, even with those resolution limits, we can get much finer printing with the photopolymerization than we do with our extrusion printing models. So yeah. So yes, it does decrease the resolution, but right now, biomaterials and the bioinker is probably the major determining factor. And actually, that's a nice segue into some of the materials that we do use to produce these higher resolution scaffolds. There's several different contributing factors that we have to investigate in order to ensure that we do get the highest resolution possible. And the first is low viscosity. Viscosity is not just important because we need this liquid to be, or we need these resins to be liquid at room temperature because they're going to cure into solid objects, but also because if you consider the fact that when that base plate lifts up, you have to have a low viscosity enough material that you have inflow back into the space where the base plate just lifted up. So that will drastically affect the printing speed. And if you're trying to include cells into a print like this, in an often environmentally uncontrolled environment, it can be very difficult to achieve good cell viability if it takes forever for the material to inflow back into that space. And that will affect, if you have a really high viscosity substance that you're trying to photopolymerize, it could potentially affect the resolution as well. And with that in mind, this kind of goes hand in hand with you still, once that material flows back into place and you're ready to cure the next layer, you need to have fast cure times. The crazy thing about photopolymerization, like I said, is you can drastically affect how much cross-linking is taking place in those scaffolds by exposing each layer to, or by adjusting the exposure of each layer. And you can get anywhere from 2 to 100 seconds that you see in these methodologies, which will, again, not only alter the mechanical strength of your materials, but it will affect cell viability, and it will affect, of course, printing time. And then we already talked about cross-linkable materials and photopolymerizable functionality. A lot of materials that we use in extrusion printing are not always readily available to use in 3D printing. So you have to ensure that the materials you use have some kind of photopolymerizable functionality that you can add to those polymers in order to incorporate them. And that gets into your choice for encouraging then that photo cross-linking reaction through a photo initiator. Probably one of the biggest challenges, if you've got a material that you can photo cross-link, is picking out a photo initiator that doesn't drastically affect the cell and still reacts at the right wavelength for your printing device. So it's really important to consider the hardware that you're working with, because you'll find some of these Vat Photopolymerization printers only work with UV light, for instance, and so obviously that will affect your choice of photo initiator. And then if you can only work with UV light, you have to pick which of these photo initiators then is going to have the least deleterious effects on cells. So like I said, unlike some of those other printing methodologies where you're just relying on you're relying on the gelation of your materials, this one gets much more complicated since you're adding these photo cross-linking elements to your print. And so you need to consider all aspects of your print because of that. Again, despite the limitations to the hardware on resolution, we often end up with the highest resolution print besides laser-induced forward transfer by using Vat Photopolymerization. And so we can get really complex structures, we can produce really nice microarchitecture, and we can drastically affect the mechanical factors or the mechanical properties of our 3D printed scaffold too by adjusting the exposure and adjusting the amount of cross-linking. So if you want to have these really nice, for instance, micro channels that have the exact right stiffness that you're looking for, you can definitely use Vat Photopolymerization to create a scaffold like that, and rest assured that you can get the microarchitecture in this printing methodology that you can't get with inkjet or you can't get with extrusion printing. Of course, like I said, the biggest disadvantage is that your material has to be photo cross-linkable. That's going to drastically limit your material choices, and the materials you use might even require solvents, which again makes things more complex when you're considering your biological interactions. And depending on the material you use, as well as the photo initiator, you may prohibit yourself from being able to use cells directly in your print. One other thing that we didn't talk about is while with inkjet printing and with extrusion printing you can use different heads, it's really complicated to print an object in Vat Photopolymerization that uses different materials. Because you're using a single vat, you have to physically switch out that vat every time you want to use a different material, and often that's not possible to do during a print and even to accommodate that efficiently. So while there is some research in using Vat Photopolymerization to print with multiple materials, you're generally not going to want to print with multiple materials. If having different materials and drastically different materials is important to you, then you're probably going to want to use inkjet printing or extrusion-based printing. So like I said, all the materials you're going to use here have to be photo cross-linkable, and the applications for this are varied. You get the typical surgical tools that you can produce with this, because you can produce pretty durable materials depending on the materials that you're using in this printing process. You can, of course, produce scaffolds that incorporate cells and biological objects, but another really interesting aspect of this printing process is that you can produce really nice tools for microfluidics or bioreactors because of that really high resolution that you can get with some printed materials. So in concluding this discussion on these different bioprinting techniques, it's really important that we also consider not just what happens during the printing process, but what happens after printing. And I like to say that 3D printing should be considered as more of a four-dimensional process because a lot of times we're so focused on getting the right printing parameters to improve our resolution and to print with cells and keeping them alive in a short period of time. But a lot of these bioinks actually prohibit some of the effects that make for producing a mature, fully differentiated tissue. And that includes things like a lack of cell-to-cell connections, questionable mechanical integrity, because all of these printing processes have limits on where you can adjust the mechanical properties of your scaffold. And none of them are going to, by themselves, produce a tissue that's fully mature and ready to implant in someone. So you need to somehow consider, how you're going to move from printing an object to, cross-linking that, gelling that object after it's printing, and how are you adding cells during the printing process or adding it after you're printing? And if so, how long do you need for those cells to mature? What's the transfer process from even something as simple as 3D printer to your cell incubator? And how do you make sure all that's sterile? It's extremely important to consider all those factors, whatever printing process you decide to use. And so in summary, I just provided this here with information on the different resolutions you can expect depending on these different printing techniques, as well as how the materials themselves are printed. And then if you want to dig a little bit more into this, there's a variety of research that has been performed using each of these 3D printing techniques in different biofabrication processes. And you can find a wealth of literature in different tissue types or tissue applications depending on which printing process you're looking at. So this provides kind of a nice summary of what people have already done and how, which printing process they've decided is useful for which tissue. So kind of the last subject that I want to get into when it comes to biofabrication is choosing what type of printer you're going to use, whether that's a commercially available one or an open source one. Obviously with commercially available, the bad thing is it used to be that to get a nice commercially available 3D printer that uses extrusion printing, you had to spend $300,000. But there's a lot cheaper printers that have just come out in the range of closer to $10,000 or even less, depending on what your material needs are. So it's really nice that we now have that availability of commercially available printers, but sometimes these printers do have limited materials and they don't allow you to work with custom materials, so you do have to consider that before you purchase a printer. I highly encourage you, if you're interested in actually getting a commercially available printer, to figure out what kind of support they offer if you're trying to use custom materials. And if you decide to go the other way, going open source, there's of course a good deal of knowledge out there on customizing both the hardware and software side of open source 3D printers. They're obviously much more amenable to custom materials if you have the time and the ability to customize your open source material or printers to the materials that you're using. So my hope is that by providing this background, you can kind of consider the goals of your research, what's most important, whether that's resolution or the type of biomaterial you're including in your bioprinting process, and how those goals align with each of these different printing processes. You want to make sure that at the end of the day, you're probably not going to be able to print a perfect tissue with perfect performance or perfect resolution, because none of these techniques can quite be used alone to do that. So you have to figure out which limitations you're okay with compromising on. And then not just deciding what type of printing process you're using, but the post-processing technique is equally as important, both in the sterilizability of your scaffolds, or in the case of, are you able to actually print in a sterile environment? You'll find that some of these printers, you're not going to be able to fit under a cell culture hood, for instance. And so you have to have some kind of strategy for the culturing and maturation of your tissue.